right, so let's continue looking at the secretary problem. So again, the secretary problem, of course, is can be generalized to pretty much anything. You know, investment selection, of course, romantic relationships, and so on. Of course, anywhere where you have some uncertainty about scores, right, on picking something, right. Of course, this can be applied. But okay, but what I thought, I just noticed a little bug, slight bug, which I fixed right now with a little hacky solution. The problem was that when we are hiring somebody, we also have a firing cost, right? But this function was not accounting for the fact for firing the first non-person. You have no candidates, you're still firing none, right? So you're basically paying for firing somebody who is not even does not exist, right? So what I did is I did a little hack. Basically, I had a negative cost. So you have extra. So the first one to fire for firing the none, you have already basically like a provision. The firing cost is included, basically, right? So of course it does not matter at all if you have zero, right? It doesn't matter at all, right? But right now you have a little bonus. So this means it will make that a little bit better for checking. Okay, and also since while I'm here, okay, I'm recording this. Let's keep increasing this. Let's add some extra features or parameters. Let's do total budget, right? So total cost and total budget, right? So maybe we can use that as well, right? I'll add total budget here, right? Total budget is, yeah, total budget. I'll do it. I'll start. Right. So higher cost. I'll make it so you can, right? Interview cost. The bug is true, and also I'll add total budget, right? Right. For now, again, we're not going to using it, but we will use it here, right? We will use it here. Total cost, total budget, right? Max budget, or maybe I'll call it max budget. Max budget. Let's rename it max budget, right? Let's refactor it. Max budget. All right, max budget to see this. We have some constraints, right? Max budget, right? So this makes things, of course, much harder, right? But again, we don't have to use this. Just means we can, for exploring this place, maybe at your leisure, you can also explore this problem and see try different algorithms for this. Now, let's see max budget. We have it, everything. Right now, our function for evaluation is extremely simple. So maybe we'll do something better. All right. So here are candidates we have. Now, will it work? Yeah, nothing changed, which of course as it should be. Right, so here it should be same, yeah. Now it's better, of course. Remember, I fixed it because I'm paying 5,000 to fire none, but I had the 5,000 bonus, right? So I don't have to. It doesn't cost me anything, right? So of course I could have added the if here. So I fixed this part here. Okay, now let's see what happens working with sorted, right? Sorted candidates, right? So your employment agency, right? They make their own. They actually, they hold a round of interviews for you because right here you're too busy, right? You're too busy with your business, right? And they give you a sorted list, but you were so busy you didn't realize they're gonna send you them in an increasing order, right? So you go, okay, send me your best candidate, right? That'd be, say, call them up, say, okay, I want your best candidate. That's it, right? But well, instead you get them sorted. So what's going to happen? You're going to blow your budget. I mean, whatever it is, right? It's going to be the worst case possible, right? So in this case, of course, right? If you have sorted, well, I need to, of course, provide is hired, right? Is hireable fund, right? Is hireable, right? This is what does this one mean? What is the total hire cost, right? This is hire cost, right? On fire cost, right? Oh no, interview cost. I think it's interview cost. Yeah, interview cost. Okay, right. Let's take a look now. Yeah. So as expected, you're gonna basically blow the budget. This is like the worst possible scenario. Well, the good news, you found the best candidate. That's good, right? But you maybe, maybe that's your like 2 years budget, basically. I don't know, right? So you are, it's really not feasible, of course, right? So, yeah. So in this case, of course, knowing this, if you know basically, if you know the distribution, then of course you can work with it, right? Again, so you could make a rule that you want at least. We could of course right let's make a function. Let's make new is hireable function. Function that will simply hire, make simply check for improvement and also for threshold score, say 0.75, right? No, you want, let's say you want 0.9, right? So it's hireable, right? Threshold 9, right? So and candidate equals threshold, and that's it basically, right? Okay, so it's hireable thresh, right? Now, right? Now we can of course basically use this one, right? And again our budget is same one, hire first. Of course now this should be much better, right? Yeah. So let's take a look. Right. So certainly an improvement, right? So again, of course, this means, of course, if you have this would be, again, if you know good scores, this would be like a reasonable algorithm. You don't really care about, I mean, assuming you have the time in the world to do all the candidates, right? You know, your N20 candidates, right? This would be normal everyday algorithm, right? Which you do in real life, right? You have some idea what a good score looks like, right? And your threshold, and you would use that. Okay, so but these are all relatively easy problems because you know the score, right? So let's see what else can you do with sorted, right? You could shuffle. Okay, yeah, yeah. But if you there's one. What you could do is, right? If you suspect a sorted list, right? You can always shuffle things, right? So throw out. So one thing of, like we saw this also. We saw this with we saw this approach with quicksort pivots, right? Where we select pivots, where we could select a random pivot. Yeah. So yeah. So that solution, of course, that pays. Of course, that involves, of course, the cost of this. Of course, good shuffling. Yeah. Is not trivial, right? So, also costs time, right? On money too, right? So, so you can say, okay, send me your random candidates. Yeah. So again, let me do this here. So knowing threshold algorithm, right? If you know that this, yeah. So yeah, and this of course is very easy, right? So okay, so but if you don't know the complete future, right? So offline, online, right? Online, of course, is meaning you have keep adding, right? You keep adding. You have to make decision, but you don't have the full. You don't have a sorted list, right? You have keep coming candidates. Maybe there's another one, right? So keep, like an auction. Maybe there's going to be more better deal elsewhere, right? So you don't know, right? So what I was going to say, maybe we'll get to this here, right? So how could we simulate this Monte Carlo method, right? Basically, we use it to estimate. We create some sort of sampling, basically scenarios, right? And then what you do is you estimate what's going to happen on average, right? Again, there are many different approaches, right? So, right, we could generate different pools, right? On different candidates. We have a random function. We only can do this, right? And we can run our higher assistant algorithm, right? And see, because in this case, we had our, we had just a simple one sampling. We probably need to run it over and over and over, right, to get an estimate, right? Simple statistics, right? And then we see the estimated cost, right? So again, law of large numbers, right? As you roll, this is a very important law. You've taken statistics, right? Or not yet? Not yet, right? So very important, one of the more important rules again. So as you roll a dice, right? Well, it's gonna tend. I mean, it seems like also common sense, right? But obviously, it will tend to the average 3.5 expected value, average value, of course. But what it means, it does not mean anything else, right? The actual each individual throw of dice still stays 1/6, right? All probabilities stay the same, right? But like I said before, if you throw a coin 100 times and it comes up heads each time, right? Well, it's theoretically possible, right? But I would probably around throw 20, 30 if you keep getting heads, right? Or your friends throwing the coin, right? You probably suspect something's fishy, right? Right?
Yeah.
Yeah, because throwing 20 heads in a row, that is what probability of what?
2 to the 30th.
Yeah, to the 30 times, yeah, to the 30th or to 20 times to the 20th. So to the 30th is about 1 in a billion chance, right? Roughly, right? So possible, right? If you have 1 billion people throwing coins, yes, there will be one good throw. There will be one throw on average, right? There will be one thrower, not necessarily, but it could happen. Maybe 2 or 3, right? On average, right? So, but it's possible, right? So, but of course, 50 coins, 50 heads in a row. There's something really fishy going on there, right? 50 heads in a row. Let's do the 50th. That probably means your coin is either really heavily weighted, or maybe you only have 2 heads on a coin, right? Right? A good old trick coin, right? Or something off, right? So, yeah. But again, the approach is right, yeah. So there's 2 things. That so the wisdom of crows, and of course there's also something called reversal of the mean, right? So you throw. It's expected that you might have some runs where you have 5 tens, 5 nines, or I don't know, whatever number you're trying to get, right? But eventually, of course, an average in a long run, it will all go to the mean, right? Expected value, right? So you can throw the dice, right? You can see the law of large numbers, of course, as you can see here. 1 million times, right? No, 10 million times, right? It keeps already, see, it keeps the limit, right? 10 throws, yeah, it could be 4, could be average, maybe, but as you throw more and more dice, your number of averages will tend to the expected, right? Okay. Yeah. All right. So we can do a simulation. Let's do a simulation. Let's see. Okay, this will be a simulation. Let's see what we're gonna do. We have total cost. We have candidates n, right? Candidate pool around the car assistant, right? Debug false, right? Let's see what the cost will be. Right, 100,000 simulations. We're gonna give higher, right? On what's random permutation. Okay, and this is using is higher, right? Yeah, this is gonna be simulation. Is hireable fun is hireable. Debug is false. Debug is false, right? Debug. Is hireable. Is candidate pool. Let's see. Is hireable fun. Is hireable fun. Right, and also budget, right? Budget. Max budget. Right. And we also want the is her assistant. Yeah, max budget. Max budget is max budget. Now let's see max budget. All right. Okay. So now we have potential to do lots of simulations. 1, 2, 3, lots of functions, right? Probably the thing is, by now, when you get so many, again, this is a code question. If you have so many flags, right, and your function gets too many parameters, right? Probably you want to put it in some sort of structure, maybe some sort of like an object type of structure or some structure if you are depending on your language, right? Because you're getting too many parameters, it gets really, you know, if you have like 50 parameters, right? Sometimes some libraries have it's kind of annoying, right? So probably some sort of object type of structure or structure which, you know, maybe you put all these inside some sort of object basically. Okay, getting too many parameters. 1, 2, 3, 4, 5, 6. Okay, now let's take a look if this works. Oh yeah, it works. And now let's see, 2000. Let's do 100,000 simulations, right? So what we'll do is we are gonna do sampling, right? We are gonna shuffle them and see what happens, right? What's the average? So we will calculate for a basic Control Z, right? So we will calculate the average cost hiring assistant using this is for the basic using this is using the basic is hireable function, right? The default one, right? Okay, let's take a look. See this 100,000 times. Let's see if this works. All right, I did not make it. I thought I did it. What is this? Simulate. Okay. Intent tuple. Okay. Yeah. All right. Yeah. Of course. Average cost is this number's total cost. Cost. This is a tuple. Cost. Best candidate. Right. Best candidate. And best score. Best score. But we don't use those, right? We don't care. We could also see what the average score is. Also, we could do that, by the way, too, right? Total cost. Score. We'll do that as well, right? Let's do score. Score. Candidate score. Total score. Total score. We will use that. We will see how well we do on the candidates, right? On total cost, and then of course best score, total score, yeah, plus best score, of course average cost and average score, right? And then we can return both, right? Now we can see how well we do on average, right? I don't know, average cost, sorry, average score, all right. Again, come on, average score. See how we do now. Okay, now. Okay, all right. Well, again, so the average cost is 24,000. All right. This is for the basic strategy. And again, not surprisingly, since our heuristic is basically to go through all of them, right? We go through all of the employees, right? Or again, all applicants, right? So of course we get the highest score. So not shockingly, not surprisingly, we always get the best candidate, right? Because because we are checking everyone, right? Every applicant. Okay. Now let's try one more time. So one more time because we have a few more minutes. Let's try the threshold. Yeah, is Harald threshold. So we'll do this one, right? Num simulations 1, 2, 3, right? See what happens now. This should be cheaper. Well, again, not surprisingly, right? Because again, so on average, what happens is basically we get basically like 1.5 times. So on average, we find this best person, you know. So obviously, so again, so knowing a good threshold, right? Right, of course, right. If you set too low, you might have to. Okay, so this is the basic thing. Okay, but unfortunately, this is all good best case scenario, right? You know what the scores are, right? But in real life, right, you don't know really many places, right? So what do you do when you don't know the scores? And this is like a kind of very weird trick, right? So this is what I have, kind of cool trick, but right. So if you, and this is like the store. This is if you create a spot, you have to. Let's say you have max, like a cost of firing is like almost infinite. Basically, it's really hard. You need to find the candidate, right? So it has to be good enough. Them have to be good enough, right? But doesn't have to be the best. But you don't also want somebody who is really, sort of bad, right? So the thing is, you don't know the scores distribution. So what do you do, right? And so there's again this kind of cool trick, right? We'll see what we know. So basically, it's been proven statistically to use Euler's constant. Euler's constant is what, 2.71 something, right? So you divide n by Euler's constant. It's called 37% rule. So you take 37% candidates and you use them to build up distribution, basically, right? So basically, they are the poor guys or girls, right? They don't get hired. They only serve as your test cases, basically. They give you sort of like the view of the world, right? Okay, which is good, which is bad. And then at 37, you say, okay, number 37, 37%, they go to the door. Thank you for your time. And then you start actually hiring because now you know the scores on average, right? And then you hire the next one, whichever meets your threshold. Because okay, you have your distribution, right? So you learn something about the world, basically, what the scores could be, right? So obviously, this is not going to be always perfect, right? But this is under uncertainty. I mean, you don't know the scores, right? Then you don't know the range of the scores. You sort of learn what's possible, right? And then you apply it, basically. So it's kind of cool, actually, because it's, n divided by e, right? So it shows up in, e shows up in many places, right? So yes, it's possible, of course, you hire the last person, right? Right. Worst case scenario, you would require 63 persons being worst, right? So of course. By now, if you have a big enough candidate pool, right, the first 36, 37 persons will give you a good, I'm talking about, of course, if you have candidate pool of 100, of course, right, to make it simpler, right? So you have 100 persons, right, so percentages are easy then, right? You strike out on the first 36, right? So then, well, right, so, but of course, like, it's possible, right? You end up at the last, none of the, nobody has a higher score than the highest score in the first pool, right? And then you had to hire the last candidate who might be kind of bad, basically, right? That's possible, right? But it's, on average, it's going to work out pretty well, right? So that's our math constant, right? Let's see if we can do this simulation. I don't know if we have time, right? Right. So let's try to see. Okay. All right. So I would like to do a simulation. Let's do a simulation. This, right? Let's do a simulation, right? Right. And now the question is, can we make this? Is our current setup going to work for this? Because we need to see when we check our candidates. We could do it, but then we also have to find. Guess what? Then you need it. You need to pass in. Could we? I guess we'll have to add one more constant. We need to add one more parameter. We need to add the index then, right? Yeah, we'll need to add the index then. Yeah, and then we can do this, or using our current scaffolding or framework, right? So that the problem is, of course, I'm doing this as we go, right? So we'll add index. It's hireable. We'll call that index, right? Index here, right? Right. Right. So best score, total cost, right? And let's see what could we add, right? Index. Problem, of course, is now how do we? We need to store some state, right? Current best, right? Yeah, yeah. Best score index. Could we somehow improve on it? Best score is good, right? Yeah, I guess we could do this index, right? Yeah, okay, I guess it would work. Yeah, okay, index will work. And index, we don't need index here. And here we are gonna call it, index is gonna be enumerate, right? For enumerate candidates, right? Right, that will work, right? Index, right? Index, right? And we can pass index here somewhat, right? Yeah, I can do that. Right. Now that works, and we'll need to also, let's see if this works. Where's my threshold? Where's my threshold? Threshold. Oh yeah. So again, index, right? Index. Yeah, it works. Still working. Okay, good. Now, let's do 100. All right, let's do it for the 100, and let's compare it now. All right. So this is fire assistant. This work. Yeah, this will work. Yeah, okay, everything still works, right? Everything still works. Okay, nothing's broken, that's good. Now we can set up our new function, hopefully. Now let's write a function that considers the index as well, right? So basically, and I guess you need total n then as well. I guess I need to add also total number, right? Total n as well. Yeah. So this gets, like I said, it's candidates, right? It's variable total n, total candidates, right? That's right. So num candidates or num candidates, right? We want that, right? We need to pass more things, unfortunately, right? And then we want this one to num candidates, right? Num candidates. If index, and what's num candidates? Of course, it's here, right? Candidates here, right? Length of candidates n equals length candidates, and we'll pass it here, right? Num candidates, num candidates, right? How was it? I forgot now, right? Equals n, right? And I'll just pass n basically, right? Yeah, okay. That looks okay. You know, no, it gets like I said, this could really use the rewrite. Yeah, but still works. That's amazing. Yeah, still works. Oh, no, this bad. Yeah, works. No threshold. Again, I need to pass this num candidates. Yeah, all right. Yeah, it works. Okay, good. Now, does this work? Yeah, it works. Everything works. That's good to know. I have not broken anything yet. Yeah, all right. Now, finally, we can, let's do this index as well as number of candidates, right? So basically, so we will utilize the enemy rules. So, right, so candidate index, so basically base score, right? And index is less than number of candidates, right? And also the question is, okay, we have again a problem. This is good, right? But unfortunately, the problem is that we are not going to save the score, right? That's the problem. This is not going to work. Why? Because we are going to skip all the rest of candidates, right? And then we will sadly, right? This would unfortunately, this will not work because we will not be saving the best scores in the N section, right? Right. So we will have to do it from. Let's do it from scratch. Maybe we can do this from scratch, right? So let's do this. Let's do it. So let's implement that from scratch. We will take a list of random list of random candidates and turn the best candidate using N rule. Right. So yeah. And the thing is, higher, right? Candidates, we don't have threshold actually, right? We're not going to use threshold at all, right? Best score, right? And we do it immediately, right? If else, right? Right. So what we do this, okay, here's the idea, right? If, yeah, all right. So basically, this is the algorithm. So this is the algorithm. Candidates, best candidate none, best score zero. We go through all the candidates. So basically, we update, we learn the learning section, right? Now the any section, right? So when we already have the best candidate, assuming all limitations, right? So then we take if index, but the thing is, if it's here, right? This part here, right? Yeah. So now if index, right? This means here we have improvement, right? Then we have need this. Unfortunately, we need the edge case, right? If also here we return, right? This is like, you know, the bad case, the final return. If we run, we run out of candidate. The thing is, best candidate is the last one, basically, right? We have to hire the last one, right? Which is not going to be. It's going to be what? It's going to be candidate, right? We have to return candidate. Yeah, and that's a bad case, right? Yeah. Yeah. All right. Now, let's test it, right? Now, to test it, we will use 100 versions. We will take 100 candidates. Yeah. Of course, All right. Number simulations, number candidates. All right, candidates. Right. I'll do seed, random seed. Right. On. Oh no, maybe we'll do this number successfuls. All right, let's take a look. Sample. Right. Let's see how many times we get the best candidate, right? Oh, I guess we can do this. Maybe it's 2.8 times. We run it pretty quickly. So 37% of time. It works 37% of time. We got the maximum candidate. But what we could do is maybe save the distribute. Let's save the candidates, right? We'll get the best candidate, right? Let's save them. Best candidates. Best candidates. Right. Right. Pen. And let's do that. That will take a little bit longer. Maybe a couple more seconds. Let's plot. I want to see the plot distribution. Let's plot the distribution. Let's plot the distribution. Let's count the best candidates from counter. Right. Let's count it. All right. Counter. Counts. Right. Right. All right. So 37% of time we got the best candidate. 14% of time, right? Well, yeah, 14% of time we got what? We got second best. Then it looks like, right? So it keeps decreasing. So we are doing pretty good actually, right? Sometimes of course we get really awful candidates like this 30%, right? Sometimes, right? So like 0.40% time, right? But it's overall it's pretty good actually, right? So we have like 50% of time we get the really good candidates, right? So this rule works. Again, sometimes you get like the worst candidate, like, you know, somebody who is really horrible, right? But again, that's the best we can do under these restrictions, right? So let's plot this. Let's plot this histogram. Let's plot the histogram of the best candidate. Yeah, plot. Let's do this. 20 pins? Do we have 20 pins? No, how many pins do we have? How many candidates we have? How many encounter? Counts? No. How many keys encounter? 100, of course. So everybody has, right? So bins 100, bin 100 bins probably. Can we do it? Plot show. I think plot show. Yeah, plot show. Does it work? Oh my god, yeah. Well, yeah, so we see some, again, this tail, right? But the costs are, we used, so 60,000 times we got the best candidate actually, right? But I wanted to actually show the distribution of these scores, maybe not in this format actually, right? So we can see sometimes we get the small candidates, right? And then, well, the best ones, we get 37% time we get the best candidate. But we will get this bell curve if we actually sorted them out. Okay, but before the break, I want to show you about the idea how you can calculate. You've probably seen this. You can calculate the pi using Monte Carlo method, right? You just throw random dots, right, at a square, right, and you can calculate the value of pi just by throwing random things. And actually, some students, like I don't know, some years ago, they did this experiment. You know, they just throw stuff on a table, right, and did it by hand, right. So now you can do it yourself, right? Just run it, and it's not a great method because you have to do a lot of simulation, but it does work actually, right? So, but just randomly, because, well, why? Because why does it work? Because of course this estimate, right? On average, right? This will be this area, right? Is bounded by the pi by the formula, right? That's why it works, right? So random points, right? And count how many points are used in here, right? inside the quarter circle, right? So that's the value of pi, basically. Yeah, you can do it here. Let's see it once. Yeah. So if I row it, so yeah, you see it works. So if 110 million, yeah, with 110 million, so 3.14, actually, it does work, actually, estimation. All right. And of course, another thing, of course, the Monte Carlo problem, that's a really fun problem, but that's probably for next time. Yeah, we don't have time for it today. All right, so what did we learn today again? So you can use, again, about the n divided by e approach. Something like that might be appropriate. So you use something, if you don't have if you have unknown distribution of data, all right, you use the 37% rule to learn something about this data, and then you can make decision on the rest of the data. And second, of course, thing is you can make these simulations using basically random simulations to create an estimate of how your algorithm will perform on average, right? The average cost. It's what usually you care about. All right. Any questions today? No. All right. We'll continue at 11:15.
Yes.
Okay.
Man jānda izčakarē mentāli. Tā es formulu vienkārši. Es nevaru tas lekcijas nosēdēt. Kad mums ir
Viņš ir problēmā, es ceru. Bet es viņu izlaidu, bet es viņu. Man tā kā
pirmdien. Jā, bet piekdien.
Nē, viņš nav nākamajā. Šobrīd ir tests. Otrais.
Es runāju par Jānis.
Nākamā piekdiena?
Jā, tas ir.
Kāpēc piekdien?
Taču eksāms ir tā,